start examining carefully first 10 pages of chapter 19, because that's where we're going to be quite soon. And as usual, if you've had a good look at what we are to talk about before we talk about it, it will sink in so much more effectively. Secondly, since we postponed the time for exam 1 to 8 days into the future, we're going to postpone the time for quiz 2 and advance that 1 week into the future. Thirdly, when last time we met and began to take a look at some of the complications or apparent complications which become part of the calculation puzzle, when in addition to equilibria and material balance, you've also got to consider charge balance, I saw a number of worried looks in the audience. Looks which said, "Oh my." Now, number one, the calculations which we looked at and which we are yet to look at, we'll begin to look at them today, are not difficult. They're not difficult. They're not even high order algebra. Number two, what I want you to be able to do is to recognize the calculations that you have to do. Understand why these calculations have to be done. But on a quiz or exam, I'm not going to ask you to go through the calculations because that takes too much arithmetic. Of course, I'd be completely at liberty to ask you to do that on a special quiz, because then you got all the time in the world. But you're not going to ever be asked to grind through a bunch of this kind of stuff on a quiz or exam. But to understand the stuff you have to grind through and why you have to grind through it, that's important. It's like in 2045. If what you do is to get a formula and shove numbers into a formula to get an answer, you practically have achieved nothing. You need to understand where the formula comes from and what the formula means and what the result of the calculation means. In other words, why did you even want to do this calculation? What has it taught you? That's what matters. That's what chemistry is about. So keep in mind, we're just trying to get you to recognize what chemistry is about, what it involves. That doesn't mean at this stage of the game you're going to have to do all this chemistry. With that, I'm quite sympathetic. And I hope also understanding. And so, let us now take a look at the last general topic of sorts in chapter 18 on acid-base chemistry, Bronsted-Lowry acid-base chemistry, which of course will invite us to consider, in addition to the pertinent equilibria, for a calculation like, let's get solution pH. Material balance and charge balance. Because as we've said, when you look at the pertinent equilibria, in addition to material balance and charge balance, you can calculate correctly if you need to do this, or if you want to do this. The molarity of any species in the system under concern whose existence depends on pH. And most all species in water solution have that property. Not all, but most all. So the heading for this is hydronium ion concentration calc for solution in which principal Bronsted-Lowry acid-base equilibrium reaction does not involve hydronium ion or hydroxide ion. Now, let me back up and restate this, because We've already looked at systems where you've got to consider, in addition to pertinent equilibria, you've got to look at material balance and charge balance, like the iron nitrate solution. But those solutions involve hydronium ion. So what I meant to say, because what I just said a moment ago wasn't quite correct. What I meant to say is this is the final aspect of solutions that we need to consider dealing with. Getting at solution properties like hydronium ion concentration, which also involve, in addition to the pertinent equilibria, material balance and charge balance. There. That's better. A solution, which is part and parcel of this consideration, is this. Or another one which we talked about last time. The ammonium cyanide solution. Because I believe last time I told you we're going to look at this calculation. We shall. But this is simpler to some extent. So we'll look at this calculation first before we go to this. But in what way these two systems relate? They relate in the fact that for either of these systems, the principal Bronsted-Lowry acid-base equilibrium reaction does not involve hydronium ion or hydroxide ion. As soon as you see that, if your task is to get system pH, you've got to pay attention to at least one more equilibrium reaction in that same system, which involves the production of hydronium ion or hydroxide ion. Nothing fancy about this statement. The sodium bicarb principal equilibrium. You know how to do this. You write the PSI. From the PSI you picked out the strongest acid and the strongest base, as necessary using the acid-base table for support, a crutch, and find out that in this system, as we've already recognized, bicarb is the strongest acid as well as the strongest base. So there's the principal acid-base equilibrium in bicarb solution. But in accord with this condition, this contains neither hydronium ion or hydroxide ion. So if we want to get pH for this thing, we got to go someplace beside this equilibrium. So I've written the other some places where we're going to go. We recognize bicarb as the principal species. So let's look at an equilibrium reaction. This is just horse sense talking to us. We pay attention to a principal species in the system and focus on the ability of this principal species to engage in a reaction which makes hydronium ion or hydroxide ion. Immediately that should tell you, we're going to look at this principal species regarding its ability to make hydronium ion or hydroxide ion. We're going to look at this species reacting with what? Water, you're damn right. That's where you're making hydronium ion or hydroxide ion. So for bicarb, here's the equilibrium reaction which corresponds to Ka. Here's the equilibrium reaction which corresponds to Kb. So we can pay attention to either of these or both. Now then, which of these is the larger extent reaction? Kb, bigger number. Now then, without doing any calculation, but now you likely know how to, and if you don't just yet know how to, when you get through the start of chapter 19, you will know how to calculate K for any equilibrium reaction. See, for this equilibrium reaction, I haven't given you the K value. But you could write the equilibrium constant expression for this, multiply it by hydronium ion top and bottom, and you'll see how to calculate K. But we're not going to do that. What we are going to do is to ask you about the extent of this reaction compared to the extent of either this reaction or this reaction. Tell me, how does the extent of this reaction compare? Reaction Roman 1 compared to the extents of Romans 2 and 3. How does the extent of this reaction compare? It's either smaller, larger, or the same, and I got a feeling you won't bet the same. How many vote larger? No looking around. Only I can cheat. Larger is correct. Y is larger, correct. That's the important part. I'm listening. Any yoppers out there?
The first one has a K of 1. The first one has a K of 1.
Oh, nowhere near.
The conjugate.
The first reaction, bicarb plus bicarb, has a K that's much smaller than 1. But nevertheless, it's a K that's much bigger than the bigger of these two Ks, which is 2.4 times 10 to minus 8.
HOCO2 is a stronger bronzillary acid and a stronger bronzillary base.
Then?
Water.
Yeah! Right? We're letting the chemistry talk to us. In this reaction up here, Bronsted-Lowry acid bicarb is reacting with Bronsted base bicarb. And Bronsted acid bicarb is a better H plus giver than water, and Bronsted base bicarb is a better H plus taker than water, isn't it? That means the extent of that has got to be greater than the extent of this, because this shows bicarb behaving as an acid, giving H plus to water. Well, bicarb is going to more readily give H plus to bicarb because bicarb is a better base, a better H plus grabber than water. Hey, this shows bicarb behaving as an H plus stealer. And it's a better H plus, and bicarb ion in this case is going to steal, up here, bicarb ion is going to steal H plus from bicarb. And bicarb's a better H plus giver than water, isn't it? Well, then that's got to be larger extent. Now, why are we concerned with that? We're concerned with that so as to realize when we write this reaction, which gives us hydronium ion, or this reaction which gives us hydroxide ion, which means we can use these to get at our pH calculation. Okay. Are the molarities of these things equal? Are the molarities of these things equal? Can we apply x squared over m sub I minus x to either of these? And the answer is hell no. Why not? Not to get a correct answer. Why not? Hey, does this thing not make carbonate ion? And the extent of this is greater than this, isn't it? So this makes more carbonate ion than this makes. Well, if this makes more carbonate ion than this makes, these molarities can't be the same. This has got to be bigger than this, the molarity of this. Now let's look at this, because this is the only source of hydronium ion, right? Now let's look at this, because this reaction is the only source of hydroxide ion in the system, only principal source. Water plus water won't matter in this system, okay? And in this case, this reaction is also making H2CO3, and this is larger extent than this. So the H2CO3 molarity is guaranteed to be bigger than the hydroxide ion molarity, because you got two sources of H2CO3, and this source is a better source than this source. So whatever the molarity of this is, it's bigger than the molarity of this. So how many unknowns we got? Uh-oh, there's where the problem lies. This an unknown? Yes. This an unknown? Yes. This an unknown? Yes. Well, we already know this is an unknown. Now, will this also be an unknown? Yes, but how can we get this as an unknown? Remember this? So if I identify this is an unknown and this is an unknown, this won't be an unknown, right? Because that's what the material balance allows us to do, eliminate an unknown. Because here, which is the material balance equation for all forms of carbonate in the system, if I identify this is an unknown and this is an unknown, this will not be an unknown, because I can solve for this in terms of these. Or if I identify this is an unknown and this is an unknown, then this won't be an unknown. Okay? Is this an unknown? If I've identified this as an unknown, is this an unknown? Why not? Isn't this the same as this? So if I identify this as an unknown, this is not going to be an unknown. Because once I get this, I can always get this with this. But we have more unknowns than we can crack. Solve for with the two or even 3 equilibrium reactions. So we got to go to material balance. We've showed you how that applies. And charge balance. Here's the charge balance expression for all species in the system. All charged species in the system. Can we set this charge balance equation equal to a charge sum? Well, before we answer that, let's go back to this. This is something we talked about before. Hey, let's take advantage of what we already know. What can you tell me about the gee whiz pH for this solution? Or put another way, before we attack this solution, the 10th molar sodium bicarb, before we attack this with calculation, let's get an idea of what we're going to look for in doing the calculation. Is this solution acidic or basic? If it's acidic, is it strongly acidic or mildly acidic? If it's basic, is it strongly basic or mildly basic? Or is it neutral? 5 possibilities exist, and I know daggone well you know only one of these applies. So if you want to start throwing darts at a board to find out which one applies, you got 20% chance to be right. And if you get it right like that, I'm going to take off 1,000 points because you got it right the wrong way. I want you to get it right because you understand the chemistry, not because you guessed it right. Now, we did this before. Is this solution, number 1, acidic or basic? It's basic because, hey, you got the data on the board you need. Doesn't KB bicarb show that bicarb's a better base than it is an acid? Bingo. So we know the system's basic. Now let's look at the magnitude, because we also want to let the magnitude of these K values talk to us. 2.4 times 10 to minus 8, that's hardly a big number. So mildly or strongly basic? Mildly, bingo. So with that, let's go back to charge balance. Question is, for this system, can I or can I not set this equal to a charge sum? Directly from the information on the bottle label. There's the bottle label. Can I? What is a charge sum? All done. Isn't that the sodium ion molarity in this system? Have we not recognized that the hydronium ion molarity for this system is lower than 1 times 10 to minus 7 because the solution is basic? Well then, damn it, there's the charge sum. All done. This is the kind of stuff you need to think about. This is the chemistry. That's what it's all about. All right? Now, the complete solution of this problem is given in a detailed step-by-step analysis in the notes. So I'm not going to repeat that. But I will ask for a couple of considerations which are in regard to this analysis so that you have a better understanding of the analysis as you look through it. We've already recognized the solution is mildly basic. And we know when we get the right values for hydronium ion and hydroxide ion and everything else in the system, that every one of these equations will be satisfied by these right values. If I put in the correct equilibrium molarities for this, this, and this, it'll add up to this. If I put in the correct equilibrium molarities for this, and this, and this, and this, it adds up to 0.10, and blah, blah. When I put in the correct molarities for bicarb and hydronium ion and carbonate ion, I'll get Ka and Kb and all that stuff. Okay? So I want to give myself an idea. What kind of equilibrium molarity am I going to look for hydroxide ion and hydronium ion for this mildly basic solution? Now, how do I pursue that? Do you remember being asked about determination of the hydronium ion concentration min and max for the iron nitrate solution? We did that one. Well, let's look at the hydronium ion concentration min and max for this system. So regarding how solve, We're following this over here. We got over here now. Okay. And an arrow from that. Okay. That's right. Consider H3O plus max. What is it? You tell me, I'll write it down. If you don't tell me, I won't write it down. Then you're stuck. What is it? Yes. Don't be so quiet. Yup. 1.0 times 10 to the minus 7. Did we not just find out this damn solution is basic? Well, it can't have a hydronium ion concentration, therefore greater than 1.0 times 10 to the minus 7. Because solution is basic. Now let's look at hydronium ion min. This is a little more challenging. Specifically because you have to know how to get hydronium ion min. Look what we got here. For hydronium ion min, I'm going to ask a question. How does this relate to the hydroxide ion concentration? Specifically, what hydroxide ion concentration value is to be used to get hydronium ion concentration min? What hydroxide ion concentration value is to be used to get hydronium ion concentration min?
1.0 times 10 to the negative 14.
Nope. I don't want a number. Yes! If we get hydroxide ion concentration max, in other words, we're saying, whatever the hydroxide ion concentration is, it can't be bigger than this. That tells us the smallest possible value for hydronium ion, doesn't it? Because we know, once you got hydronium ion, you get hydroxide ion, or vice versa. That's what KW allows us to do. Good. So I'll just write this down. Okay? How do we do it? So you're moving up the line. You're now getting to be where you're going to be, let's see. See, in chess you go from Class D to Class C to Class B to Class A to Expert to Master to Senior Master to Grandmaster. I made it to Expert. But my greatest accomplishment was in undergraduate school. I didn't care much about chemistry. I liked playing chess. I still like playing chess. But I had to realize my limitations. Undergraduate school for me was, one of my undergraduate school years was 1963. In 1963, or maybe it was 1964. It was in 1963 that I played the guys that I'm going to tell you about in a moment. 1964 was the only year that the U.S. Intercollegiate Chess Team won the International Intercollegiate Chess Competition. They won it because the competition that year was held in Israel, and the Soviets refused to send the team to Israel. Because if the Soviets send a team, then that's all over. Because they're all grandmasters. They were far and away, as a group of people, the best players. But at that time, the best player in the world was Robert James Fischer. In any case, the 4 guys who were the members of the U.S. Intercollegiate Chess Team, which won the World Collegiate Chess Championship. 4 guys. Of these 4 guys, 1 was a master, 3 were senior masters. I played each one of those guys in 1963 in tournaments held in the Ohio, Illinois, Michigan region of the country. I won 3 and drove 1. I was pretty damn good in my day. Now, I'm still pretty good, but I'm slow. The computer just doesn't run as fast as it used to. So, I still enjoy the chess a lot. I go to chess.com on the web. I look at the best games. I look at the stuff by Magnus Carlsen, who's now the greatest player in the world, strongest player in the world, who I'm sure is going to kill the reigning world champion with the match they're going to have for the world championship in March. That's Vishnawatan Anand, who is an Indian fellow. Damn good, you bet on that. But Magnus Carlsen is, he's amazing. 23 years old. This guy's as good as Fischer. But in any case, I'm saying right now, Class D, you're probably Class A. You're getting there. When I get done with you, you'll at least be experts. I mean it. I'm not kidding. When you go off from here in analytical chemistry, if you go there, organic chemistry, go there, you're going to be well prepared. And you're going to do well. Because, damn it, one of the most important functions of this course is to prepare you for success in the future. This course doesn't do that, then this course is a failure. And I want you to be successful, damn it. Hey, you're America's next bunch of leaders. Or at least potentially so. I want you to take from this gathering as much as you can possibly take from it. That's what it's all about. All right? Hydroxide max. How do we get it? Do you see this is the only equilibrium reaction which gives hydroxide ion? So do you think getting hydroxide ion max might have something to do with this equilibrium? Good. Now, how do we treat this reaction to get hydroxide max? We focused on equilibrium number 3 because that's the only one that's got hydroxide ion in it. What are we going to apply to equilibrium number 3 to get hydroxide max? Yes! Because this recipe neglects the H2CO3 which comes from up here. It says that we're going to treat this as a smaller value than it really is, and this is a larger value than it really is. You see the chemistry which follows with the statement I just made? So, with the application of x squared over m sub I minus x to this, we get hydroxide max, from which we will calculate hydronium ion min. Now you'll see the result of this in the notes. It gives hydronium ion min of 2.0 times 10 to the minus 10. Because when we get hydroxide max, we just use Kw over hydroxide ion to get hydronium ion. You now know the arithmetic to do. You can grind through the arithmetic yourself. So there's our boundary conditions. Now tell me, what would you do next to crack this puzzle? Because I'm going to approach it by a common sense speculation technique. I'm saying to myself, I know the hydronium ion molarity in this solution is smaller than this number but bigger than this number. That's the box, that's the range. Where should I go first to find the correct hydronium ion molarity? Well, if I don't know what the hydronium ion molarity is, other than it's in this box, I'm going to pick the hydronium ion molarity that's in the middle. That's where I'm starting first. Isn't that like 50% ionization? How do you get the hydronium ion molarity that's in the middle? Hint, you did this in assignment 1, 46L this term, or whenever you took 46L. You have to get the hydronium ion molarity, which differs from the upper value and the lower value by the same factor. And that's not quite easy to do with simple arithmetic. Because if you think the hydronium ion molarity that's halfway between those boundary values is got by adding those two boundary values together and dividing by 2, you're dead wrong, because concentrations relate to each other exponentially, not linearly. Aha! But so let's take advantage of the most beautiful aspect of logarithms. Aha! You think logarithms were invented just to make your life miserable in high school math class? You probably say, hell yes. Why were logs invented? What's the most beautiful aspect of logs? Arithmetic aspect of logs. The most utilitarian aspect of logarithms. To take exponential equations and convert them into linear equations, which can be solved by addition and subtraction. Nothing more. How about that? So, just like you did in assignment 1 in 46 laboratory, I'm going to look at this and say, the pH for this system can't be lower than this because it's basic. And the pH for this system can't be above the pH that corresponds to this number. Okay? And the pH that corresponds to this number is 10 less the log of 2. And the log of 2, the 4 significant figures, is 0.3010. I told you this stuff before. So here comes the fancy arithmetic. Since I'm only working with 2 sig figs, I will write the log of 2.0 as 0.30, and I'll subtract that from 10.00, and I'll get 9.70, all done. Those are my pH boundaries. That's the way to do it. The information I just used is given to you at the start of chapter 18 in the notes, the chapter we're still in, with my attempt to remind you how pH arithmetic can be done here, not this way. And then it'll make a hell of a lot more sense to you. You commit to memory the logs of the numbers from 1 to 10. Whole numbers. That's all you got to do. Log of 1 by definition is 0. Log of 2, 4 sig fig, 0.3010. Log of 3, 0.4771. Log of 4, I don't need to remember because that's twice log 2. Log of 5 is 0.6990. Log of 6, I don't need to remember because that's a log of 2 plus the log of 3. Log of 7, 0.8451. Log of 8, I don't need to remember because that's 3 times the log of 2. Log of 9, I don't remember because that's twice the log of 3, and all done. Because the log of 10 is 1.000. How long is it going to take you to learn that? 5 minutes if you make up your mind to do it? No more. And then I showed you the other trick about doing logs, but let's move on with this. You can take a look at what I'm talking about. It's in the notes. All right? So we'll do this. Pardon me. So now we'll proceed with these pHs. They get the mid. So, halfway hydronium ion equals hydronium ion at what pH? 8.35. Because these things, these logs, you can deal with linearly. And the halfway pH is 8.35. So I'll get 8.35. Figure out the hydronium ion concentration. Now I'll use the calculator because this is not one of the things that I've remembered. And I will find out that this middle hydronium ion concentration is... Where are you? You're in here someplace. Ah, yes. 4.5 times 10 to the minus 9. And guess what? For this particular solution, that's the answer. How about that? You will, of course, find that when you put the hydronium ion molarity in here, from which you get the hydroxide ion molarity, from which you get the molarities of the other carbonate-containing species, and you find out every equilibrium constant is satisfied. It's in the notes for the arithmetic. Interesting. It happens to be the case that this halfway hydronium ion is correct, because for this solution, the H2CO3 molarity and the carbonate molarities are equal. Serendipity. Mother Nature made it that way. I will bet for no other solution this property exists. All right. Now then, two more things we want. Well, before we do a couple more things, let's go to question 1864. Actually, no, we already did question 1864. Question 1864 is about this. But it won't hurt to ask it again. As beneficial review. If we wish to set about the task of computing the hydronium ion concentration for ammonium bicarb, we're looking at a system which problematically is just like this. Because the main acid-base reaction is ammonium ion plus bicarb ion. Doesn't involve the production of hydronium ion or hydroxide ion. So what are you going to have to look at in this system? Well, your best acid is ammonium ion. So you're going to have to look at ammonium ion plus water makes hydronium ion and ammonia. Or you're going to look at bicarb ion in this system behaving as a base. So you'd look at this. Okay. But without doing the arithmetic, since we have this as the hydronium ion concentration, as the known hydronium ion concentration for our 0.10 molar sodium bicarb solution. What do we know about this ammonium bicarb solution compared to the sodium bicarb solution? Is the ammonium bicarb solution, for example, basic? Do you know that Ka ammonium ion is 5.6 times 10 to the minus 10? So is the ammonium bicarb solution basic or acidic? Basic. Because there's Kb bicarb, and that's a bigger number than Ka ammonium ion. Now, will this solution be more basic or less basic than the sodium bicarb solution? More basic or less basic than the sodium bicarb solution? It'll be less basic. Why will it be less basic? because this guy is a stronger acid than bicarbonate. Okay? So, if I want to tackle this one by calculation, we will know this. It has the same hydronium ion max as what we did up there, because this solution is also basic. And what can we write down straight away as hydronium ion min for this thing? The answer's on the board. Can we write this? Can we write this? Yes. You're damn right we can write this. We know that this solution is less basic than our sodium bicarb solution, and we know this is the hydronium ion concentration for the sodium bicarb solution. So, we'll do this. Hey, take advantage of what you already know whenever you can. Nothing wrong with that. Okay? So then you could proceed. Now then. Let me write on the board the problems we're going to tackle when we next get together. Calc. Hydronium ion concentration. 4. Because what these last problems will bring together is everything of consequence in Chapter 18. (5.0 times 10 to the minus 6) ammonium sulfate solution. And then 5.0 times 10 to the minus 7 acetic acid solution. And then at last, the 10th molar ammonium cyanide solution, which we talked about last time, and which we said last time we will eventually get to the hydronium ion computation. Now that's what we're going to finish up with on Monday. Take a look at this stuff. By now you can handle every one of these cases if you focus on what we have so far considered.